Hello, everyone, and welcome back. Today, we'll look at a new topic, which is numerical integration. Now, we have done numerical differentiation before, right? Finite differences. We have looked at how, different ways to calculate delta as well as gamma. So that's numerical differentiation using finite difference. We'll see the application in pricing in future. Today, we'll look at numerical integration. Okay. So, right. Now, what is the motivation for learning numerical integration? Why should we learn numerical integration? Okay. And when it is required? Well, you resort to numerical recipes when you don't have any analytical formula, right? So up until now, whatever integration we've been doing, the result of an integration is always a known function. Okay. You integrate 1 by x, you get log x. Log x is a known function, well-behaved function, right? So till now, whatever integration we have looked at, the result is always some elementary function that we already know. Okay. Sometimes there will be integrations which do not have a closed form answer, right? Integration exists. So I'm talking specifically about definite integral. So what is integral after all? Integral of a function is just the area under the curve, correct? So if you're trying to perform indefinite integration, essentially you're trying to calculate the area under the curve. Area under the curve exists. If you can draw the curve, then there is area under that curve. But sometimes you're not able to find that analytically, okay? So in those situations, we will fall back on numerical procedures. And how do we go about it? So basically, right, if you want to evaluate an integral and there is no analytical expression that exists, in this case, we resort to numerical techniques. What we'll do is we will divide the interval over which we are trying to perform the integration. We'll discretize that interval into smaller segments, or those are called as sub-intervals, and then calculate the area of those regions, okay, so over that small interval, and then add them, add everything. That will give you an approximation of the area under the curve, which is nothing but the integral. Okay. Now, for a quant finance student, when typically we run into these kind of situations, I've listed down two classical requirements for which we definitely need to know numerical integration. Numerical integration is probably one of the most top three numerical techniques that you would need in your toolbox. Okay. So you have to know this. This is very important. Okay. The first example is, it's a very simple use case. How do we find the cumulative probability under a normal distribution? Okay. So we'll talk about CDF and PDF in the next class. That's the last, probability would be the last primer, and then we'll get to the core stuff after that. So if you want to find out the CDF under a normal distribution, essentially you have to integrate the density, right? Integration of e to the power minus, so x square by 2 from minus infinity to x. There is no closed form formula for this. Okay. You cannot express this in terms of the elementary functions. So there is a numerical procedure based on which you have to perform this integration. And people have already done it, and they have given us the table that we always look up to find the cumulative probability given a z-score, right? So this is one example. And the second thing is, when do you run into integration? Well, when it comes to derivative pricing, probably the single most elegant formula that has been developed as a pricing tool is expectation. Okay, so we'll see it later that price is given as expected value of discounted payoff of a derivative, and the expectation is a special expectation. It's not based on the physical density, it's based on something else, risk neutral density. We'll see all that later. So we will need to calculate expectation many, many times. Okay. And expectation is nothing but an integral. It's a definite integral. Okay. So if this expectation, I mean, expectation, which is an integral, you're not able to calculate analytically, then you have to go to numerical procedures. Okay. So that's where you also use numerical integration. In fact, when we learn about Fourier techniques to price an option, we will require numerical procedures to find the area under a curve, okay, or perform integration. So two very basic examples for which we will need to perform numerical integration. All right. Topic is very easy. It's just basic geometry and some implementation routine that you need to know about. Okay, let's familiarize ourselves with the basic setup. So our requirement is this. We want to integrate a function f of x from a to b. Okay. Geometrically, it looks like this. So we have x-axis and y-axis. This is the interval. So this is the function. The orange line is the function. Integration of f of x dx from a to b is nothing but the entire area under this orange curve. The entire area, right? Okay. Are you with me so far? Any questions, guys? All good? Okay. So what we need to do is divide this segment A to B into n sub-intervals. N sub-intervals. Okay. Now I will label this all these points on x-axis as xi, right? Starting with the first one, which is A. A is the first point, right? That I have to, so the master interval is A to B. I have divided it into n sub-intervals, okay? So my x0 is A, correct? x1 would be A plus whatever the width is. The width for now, let's call it as h, all right? And this h is same everywhere. It is uniform spacing, equal width subintervals, at least for now. So what is h actually? If there are n steps, then I can easily write h is equal to b minus a divided by n. This is the total interval, and then divided by number of subintervals. That gives you the width of each subinterval. So if x0 is a, that's my first point in the interval. x1 is a plus h. x2 is a plus 2h. Okay. So what is xi? Xi would be a plus ih. Okay. Instead of a, I will write x0 plus h, x0 plus 2h, and x0 plus ih, right? And it goes on, and the final coordinate xn here, which is nothing but b, and that will be given as x0 plus nh. Okay. If you put h equal to b minus a by n here, then you actually get back b. You can just quickly verify that. All right. Any questions, guys, till now? Also, a quick audio check. You guys, can you guys hear me properly? Okay, looks like there is some lag. All right. Okay, I'll just assume that this is all basic stuff. So if you have any questions, let me know. So how do we come up with the area under this curve? The idea is you just add all these areas. This plus this plus this plus this, all the way till the last one. Just add all these areas and then you get the total area. That's the answer to this definite integral. Okay, so that's the basic idea, right? So the next step would be, how do we go about calculating the areas? And then simple addition is fine, but how do we calculate these small areas? Okay, so yeah, these are some of the equations that we developed, right? X0 equal to A, Xn is equal to B. There are n steps in total, and every sub-interval has a width of B minus A by n. Any point you can express as this, X0 plus IH. Okay, right. All right. The first and foremost important idea is a Riemann sum. Okay, Riemann is one of the most famous mathematicians of all time. So as per him, a definite integral can be seen as a Riemann sum. Okay, this Riemann sum again we'll revisit when we talk about Brownian motion in stochastic calculus. So the approximation formula under Riemann sum is given as, basically the idea is each of these small regions that we looked at, right? Treat them as rectangles. So this is indirectly all rectangles. So rectangle uh, aggregation. Okay. Now, how do we add these rectangles? Let me draw this picture here so that we can develop the idea. Okay. So we have y equal to f of x. This point is our first point A, which is nothing but x0. And this point is our last point, which is nothing but xn. Let me draw a couple of them. So this is x1, equal spaced, okay? x2, and then xn minus 1, right? And in the middle somewhere, we can just take any general segment. Let's call this xi minus 1, and this is xi. Okay, and there are a lot of these different subintervals. Now, under Riemann sum, we are trying to view these strips as rectangles. Okay, rectangle is supposed to be like this, but each and every segment is looking something like this. So obviously, if you want to approximate this one as a rectangle, there would be some approximation error. And it is very obvious that if we increase the number of steps, then these strips will get smaller and smaller and smaller, and they will better approximate the rectangles. Okay. So we'll see that. Now tell me one thing. What is the area? So let me write the total sum of areas is equal to what? Tell me the area of the first region. If we pretend that this is a rectangle, then what would be the area? And each of these width is actually just h. Okay. And I can write h equal to b minus a by n. What's the area of the first strip? I'll also need the height at these points. Okay. So let me call this as y0, y1, y2, yi minus 1, yi, and yn, yn minus 1. All right. yi is f of xi. So area is, for area, we need the base and the height, right? Rectangle area is base times height. The base is h always for each of these rectangles. But what is the height? In the first region, there are two heights available to me. One is y0 and the other one is y1. Okay? Two heights available to me. Which one should I take? There is a choice, of course. I can take the left one or I can take the right one. Okay? So let's say we take the left one as the height of each of the each and every rectangular strip. So the first area would be h times y0. Okay. Second one would be h times y1. And this goes on. And we have the final one would be h times yn minus 1. That's this one. Okay. Now, just so that you understand the fit, what we are trying essentially is we are taking this rectangle and then this rectangle. Okay. Now, question to you: if I use this definition of taking the rectangles, then would I underestimate the area or overestimate the area? As per this particular, others please participate. As per this curve, I am missing out a few pieces of the slice, right? So definitely we will underestimate. However, if the curve was downward sloping, then we would overestimate. I'll let you draw that figure and think, but yeah, we are kind of, yeah, we're missing out some of these triangles, small triangles. So this will be an underestimation as per this particular curve. Okay. All right. So I can just write this as h. The h is common, summation of I equal to 0, or let me not take 0. Let me take it from 1. I equal to 1 to n y I minus 1. Okay. So this is the formula that I can use to calculate the Riemann sum or the area under the curve. And this one is called as the left rule, S left. Because for every region, there are two choices of heights available, and I'm taking the left one. So this is the left sum. You can say left sum. Similarly, we can calculate a right sum. For right sum, what we'll do is, look at the first region. The area would be h times, I choose the height on the right side of the interval, okay, y1 plus h times y2. And finally, h times yn, okay. So how is the plot for the right sum? If you look at the first region, the rectangle that I'm taking is this rectangle. For the second one, I'm taking this rectangle. All right. And for the last one, you can say I'm taking this rectangle. So the green rectangles add up to the the right sum. Okay, so I can write this as h summation y I equal to 1 to n. Same thing. As per this figure, we will overestimate the area. Correct? Okay. So yeah, we got this. Any questions so far? Is this understood? We're slowly building up. A little later, we'll see some sophisticated stuff. Are we good so far? Okay. There is one more thing I can do. Instead of left or right, I can take the midpoint to be a little more precise, right? Because if we are taking the left sum, we are missing some of these small triangles. If we take the right sum, we are adding unnecessary areas into the calculation, okay, which does not exist. There are some part which is above the curve. We should not include those in the triangles, okay? So why not use maybe midpoint? That may improve accuracy. So when I'm saying midpoint, so let's say this is xi minus 1, this is xi, and my curve is suppose like this, okay? I'm focusing on one specific subinterval. What I will do is, there are two ways to achieve this midpoint idea. For now, we'll look at one specific idea, which is don't take height on the left or the right, take the height at the midpoint. And then, let me use another color, maybe this one. Now, this is the rectangle that I will take. Okay, this is the midpoint scheme. And you can see that on the left-hand side, we are adding some extra area, this part. But on the right-hand side, we are also missing some area. So overall, maybe we are accurate to the exact value. How would I write this? Sum mid is equal to, what is the first area? Who can tell me? H times what? Is it going to be, so here's a tricky question. Pay attention. Should I write H times y0 plus y1 divided by 2 or something else? What is the first area if I use the midpoint rule? Should I write H times y0 plus y1 divided by 2? H times y0 plus y and y1 divided by 2. That is not correct, actually. So in this picture, see what I have done is, first take the midpoint of x, then calculate the value of the function at the midpoint. We are not averaging height of y0 and y1. We are not evaluating the height of the function at xi minus 1 and xi, then taking the average. We are not doing that. Look at the picture. First, you take the midpoint of x, of that region, okay? And then evaluate the function, the value of the function here, which is at x mid, what is the value of the function? That becomes the height of the rectangle. Okay, small difference. So it will be h times function evaluated at x0 plus x1 by 2. It's not y0 plus y1 divided by 2. Make sense? Second one will be h times f of x1 plus x2 divided by 2. All right. And this goes on. Ith term would be h times f of x minus 1 and xi. So you average the x, find the midpoint of that in the x domain of that in subinterval. Then what is the height there? What is the height there? And this goes on. We have h times f of xn minus 1 plus xn divided by 2. Okay, so this is the midpoint rule. Now let's look at all the implementation of all of these in Excel so that we can appreciate what's going on. Right. Before this, so I have given the some pictures here for your revision. Okay. All right. So this is Riemann sum. What we'll do is evaluate. So this is our function f of x equal to x square, a very simple function. Obviously, we will not use numerical integration to perform definite integral of this one. But I have taken this so that we know exactly what the true value is, and then we'll compare the performance of the numerical integration. So our task is to evaluate integral x square dx from 0 to 2. Okay. What is the exact value of this integral? Exact integration is x cubed by 3. If you put the upper limit, it is 2 cube by 3, which is 8 by 3, minus 0 by 3, which is 8 by 3. Okay, this is the exact value. First, we identify our parameters. The lower limit a is 0. Upper limit b is 2. Okay. Number of steps is up to me. I can change that. Right now, I've taken as 4, but I can change it. Tied to this number of steps is the width of the subinterval. It's equally spaced. H is equal to b minus a by n, right? So it's just 2 minus 0 divided by 4, which is 0.5 each. So I have 4 steps to cover from 0 to 2, and the each step size or width of subinterval is 0.5. So here is my index. I goes from 0 to 4, right? Corresponding to that, I have x0, x1, x2, x3, x4. x4 is nothing but b. x0 is nothing but a, right? Okay. So to do the left sum, I will need to do what? Add uh, add all the yi minus 1. Okay. So let's go back. What I've done here is evaluated the f of x at each of these x values, right? F of x is nothing but x square. So at x0, the height is 0. At x equal to 0.5, it is 0.25. It's just square. For the left sum, you need to do h times which heights you will take. You'll take this one, this one, this one, this one. We have 4 rectangles, right? And you only take the left one. So this is my first interval from 0 to 0.5, correct? x0 to x1. I have y0, y1. I just take the y0 one, y0, not the y1. Okay. In this interval, the height is 0. In this interval, the height is 0.25. In this interval, the height is 1. In this interval, the height is this. That's all. So for left, I've basically taken h. This is h times sum of these 4 quantities. All right, and that comes out as 1.75. Let me just do it here once so that sum of these 4 times height 1.75. Okay. For the right sum, I need to, the regions are the same, but I need to take the height on the right side. So I will use, for this interval 0 to 0.5, I will take this height on the right side. In this interval, I'll take this height. In this interval, I'll take this height. In this interval, I'll take this height. So the second one would be sum of these four, correct, times height. Not height, the subinterval width, okay, 3.75. Now to calculate the mid sum, I need to first take the mid x. Here is the trick. Don't do a mistake here. First, you have to take the average x. So in this first interval, 0 to 0.5, the midpoint is at 0.25. In this interval, the midpoint is 0.75. So calculate the midpoints of each region, okay, and evaluate the function at those midpoints. So height at the midpoint is x square. So 0.25 whole square, 0.75 square, whatever it is. And then the formula would be base times sum of heights at the midpoints. So these are the rectangle heights, correct? So that's 2.625. Any questions, guys? Is this understood? Okay. Yeah, if you don't say anything, I would assume that you understood this. All right, let me delete these. Now you trust these answers. So if you see the error is defined as actual value minus the approximate value. So the difference is the error. Okay, this minus this. Now we saw, so x square is also an increasing function, right? Increasing function. So left sum would underestimate the area. Right sum would overestimate the area, you can see. And middle sum would be little accurate. And you can already see it is very, very, with only 4 steps, right? We divided the region into 4 steps. And the middle sum is doing a great approximation to the actual value. The error is much less. Okay. Now I can do one thing. I can increase n. Number of steps I can increase. Accordingly, the width will decrease, right? B minus a by n. So obviously, if I increase n, this will converge to the true value from the bottom. And this will come down and converge with onto this value. And this is just hovering around this value, right? And it will become more and more accurate. So let's see that. If I increase another step, right, I'm getting closer and closer to the true value. You can already see the middle sum is doing a great approximation to the actual value. These guys are still trying to converge, right? And yeah, so let's say we are using 50 steps. The approximation looks like this. These are the error values. Okay, I can probably go up to, let's say, 90 steps, maybe. These are I mean, still they have some catching up to do, but middle sum is doing a great job. Okay, so given a choice between these 3 schemes, which scheme will you use for numerical integration to be on the safe side? Obviously, middle sum, right? Okay, is there a theoretical result that tells us the errors in these algorithms? Answer is yes. Answer is yes, and I have given it here. So the left-hand rule, not left-hand rule, left rule, right, which takes the height on the left point to be the height of the rectangle. So x star is xi minus 1, basically, that enters into this. So the convergence rate is h square. So h is the thickness, right? The smaller h you take, obviously the error will go down. But at this, the rate is h square. So the convergence happens as a square of the step size. Okay, so imagine if you use a lot of steps, h should be very, very small. It will be a fraction, so it will be fraction square, so even smaller. Right rule, left rule have exactly similar convergence pattern. One will underestimate first and then converge to true value. The other one will overestimate and then come down and converge. If you look at the middle rule, that has a convergence rate of h cube, which is even smaller, so smaller error, right? Because h would be a fraction, so cube of a fraction, it is much more smaller. So yeah, that's the theoretical convergence rate of these three schemes. These are important to know, right, before you apply. Okay, so yeah, let's go on to the next algorithm, which is also very, very popular, is called trapezoidal rule. Okay, trapezoidal rule. As the name suggests, each of the regions is to be taken as a trapezium or trapezoid, whatever it is. And then you know the area of a trapezium. For trapezium, we have something like this. Okay, so let's say this is yi minus 1. This height is yi. This is xi minus 1. This is xi. Thickness is always h, right? What's the area of this trapezium? It's given as half times base times sum of parallel sides. Sum of parallel sides is yi minus 1 plus yi. Okay, that's the area of the trapezium. Half times width times sum of parallel sides. I can rewrite this as h times yi minus 1 plus yi divided by 2. Now, this is the one that Sachin was mentioning last time. Here we are taking the average of y's. Okay, evaluate y at the left side, evaluate y at the right side, take the average of the y's. So two times you have to calculate the functional value, then take the average, multiply with height. It is not same as evaluating y at the midpoint of x. Okay, so there you need to find the midpoint of x first and then find the value of the function, one value of the function there. Here you have to evaluate it twice at both edges and then take the average. Trapezoidal rule indirectly does that. Okay. Right. So yeah, that's all there is. So all of these are trapeziums. Now, if you look at the formula, what do we get? See, S is equal to, or should I do it there? Let me do it there so we have some consistency. So second scheme we're looking at is trapezoidal rule. And we have this setup. We are joining these points by using a linear interpolation indirectly. Because if you're using trapezoidal rule, that is what you're doing, right? Each of these regions is now a trapezium. So it's a straight line. I mean, there has to be four sides, right? Side 1, side 2, side 3, side 4. That's all. So this is x0, x1, x2, xn minus 1, xn, y0, y1, y2, yn minus 1, yn. Area of this first trapezium is, so I can just directly write h by 2 sum of parallel sides, which is y0 plus y1. Second one would be h by 2 y1 plus y2. Correct? Just averaging the y's at both ends. Plus blah, 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 blah. H by 2 yn minus 1 plus yn. Okay, that's the formula under trapezoid rule. Now, if you see this, you can take h by 2 common. Now, one thing you can notice that the first point and the last point will come only once because it is not shared. This height is not shared with anything, and this height is not shared with anything. So I can do one thing. I can club those together, y0 plus yn, first and last. Every other term will come twice. Y1 will come here, y1 will come here, y2 will come here, y2 will come here, right? So I can write 2 times all the other values, y1 plus y2, yn minus 1. So this is the formula for trapezoid rule. It's very easy to program this also in any coding language, right? This is how you need to sum. Okay. So when I'm trying to aggregate, what I'll do is I'll take h by 2 times all of these y coordinates starting from y0, y1, y2, y3 up to yn. There is yn also. All the y values are there. They have respective weights. Okay. Y0 gets a weight of 1. Yn also gets a weight of 1. Weight means coefficient. All the other y's get a coefficient of 2. Okay. That is what I have to ensure. And then just do a sum product. That's all. So let's see the implementation in Excel. It's very easy, straightforward stuff. So for trapezoid rule, what I need to do is, again, 4 steps, same integral. This is my formula. We don't need this. This was for the midpoint rule. We need mid of fx, which is average of f of x. Right. So what I've done is, for the first interval 0 to 0.5, multiply the average of f of x, which is y0 plus y1, y2, which is 0.125. Okay, average of these two. Then for this interval, this take the average of these two, that's here, which is the height. Okay, like that. And you can also use this formula also. I have done it in a later slide, but it is the same thing. Okay, and use these heights and the width. So this is simply h times the average heights for each and every interval. So sum product of, there is no sum product, h times sum of this. And that gives you 2.75. Okay. So you'll have this Excel to play with. Your task could be to code it in Python though, because it's very rewarding, right? To handcraft these algorithms in Python. It's very, very useful. Okay, so we got 2.75. The other one, the midpoint rule, for 4 steps, same 4 steps, is giving us 2.625. Which is more accurate? Which is more accurate? And you also see the error. The error with the midpoint rule is 0.04167. The error with trapezoid rule is, in absolute terms, it is 0.0833. So which scheme is more accurate? Midpoint rule. Midpoint rule is, and in fact, this is more accurate. But in popular literature, you'd strangely see that pretty much the community leans towards trapezoid rule. At least in credit risk, I have seen they use trapezoid rule for all kinds of things, calculating the area under ROC curve and things like that. But this is a little inferior to the midpoint rule. Okay, so given a choice between these two, you'd rather use the midpoint rule. The error is exactly half, actually. If you see this is double of this. Okay, but this is extremely popular deterministic numerical integration procedure to approximate the area under the curve. But this is little better. Okay, any questions? Clear? Let's move on. So next we'll look at something even more sophisticated. Okay, please remember, trapezoidal rule basically does a linear interpolation between the points of the curve because it's a straight line, and then the whole thing becomes a trapezium, so it approximates the area. Now we'll look at Simpson's one-third rule. Okay, there are two flavors to Simpson's rule. One is called one-third rule, which is what we'll look at next. And then we have something called as 3/8 rule. Okay, one-third rule and 3/8 rule. 3/8 rule, although theoretically more accurate, but it is much less popular. And there are different conditions under which one would be superior to other. So the whole industry leans towards this. Actually, this is much more popular. So we'll look at this. Now, you don't need to look at the derivation. I'll give you the final formula. You need to understand the key difference between, let's say, trapezoid rule and Simpson's rule. So remember, in trapezoid rule, we did this, right? For any segment, you do a linear interpolation, and this becomes a trapezium. That's trapezoidal rule. Okay, you need any 2 points to perform a linear interpolation. In case of Simpson's one-third rule, you actually need 3 points. Say it's my curve is something like this. Okay, you need 3 points. What Simpson's one-third rule does is it tries to fit a parabola in the 3 points using those three points. Not exactly this actually. Wait, let me see if I can. Okay. It will be a symmetric parabola, but passing through the very hard to draw for me, but something like this. Okay, maybe you can look at this picture. So let's see. So this is our x0, x1, x2. We need 3 points, okay? Because we are doing a parabolic interpolation. For that, we need 3 points. We are fitting a quadratic equation, ax squared plus bx plus c. Okay, we have three free parameters. There is a, there is b, there is c. So we can fit 3 points. For linear interpolation, you need only 2 points. So if you see these 3 points, right? It tries to fit this parabola. See the dotted line? Interpolation parabola that goes through these. The black solid line is the function, true function, and it has all kinds of squiggly behavior. But take the first 3 points, fit this dotted one, which is the parabola, right? Passes smoothly through the 3 points. And then here is another side. So these are the 3 points. This is the true function, but the dotted one you see, the dotted one that has been fitted is the parabola. So it's a quadratic interpolation scheme. Simpson's one-third rule uses a quadratic interpolation. And there is derivation behind. So basically you have to solve for A, B, C based on the fitment and then find the area under the curve, then aggregate, and ultimately that leads to this final formula, which is h by 3. Okay, so this is how to remember h by 3 outside. It's a similar pattern, just the weights are different. Okay, we have y0 and yn. Remember, in trapezoidal rule, we had the same thing. Y0 and yn, correct? Here we have h by 2, there we have h by 3. In fact, it's called one-third rule because there is a 1 by 3 at the, here, outside. That's where it gets its name from. We have y0 and yn, okay? Then 4 times odd heights at the odd places, 1, 3, 5, 7, okay? And 2 times all the even heights, y2, y4, y6, y8, up to yn. Okay, now, the very important condition for Simpson's one-third rule is that your choice of n is now restricted. Okay, for rectangle rule, which is the Riemann sum, or the trapezoidal rule, we had no restriction on n. You can have any number of subintervals as you want. It can be odd, it can be even, it can be anything. In case of Simpson's one-third rule, n has to be an even number. You cannot have odd number of intervals. Okay, so you break it up as either 4 or 6 or 8 or 10 or 60. Okay, so n is even. If n is even, then this n minus 1 term is odd, and that this is the odd group. This is the odd group, and this is the even group. Since n is even, the last term is also I mean, it's the even location. Okay, so this is the formula. All right, let's implement this algorithm unless there are any questions. Simpson's one-third rule, same integral x squared dx. Okay, this is the exact value. This is our formula. Okay, h by 3 times first height plus last height. They receive a weight of 1. All the odd places receive a weight of 4. All the even places receive a weight of 2. So basic is scheme is very simple. You have all the so I only have n equal to 2. So 2 segments. 0x goes from 0 to 1, then x goes from 1 to 2, right? Evaluate the functions, which are the y's, y0, y1, y2. The coefficient of the first one would be 1. The last one will also be 1 because y0, yn, right? The intermediate ones you have to check. If it is an odd position, so this is y1, that belongs to the odd group and it has a coefficient of 4. Since there is nothing else, I stop here. But if there are even places, all the even places will receive a weight of 2. All the odd places will receive a weight of 4. And then you do a sum product. Essentially the coefficient times the y's. So you get the stuff in the bracket, right? Times h by 3 at the end will give you the summation. Now, if I do it here with, so, and one more thing, can I take n equal to 3? Question to you, under Simpson's one-third rule, can I choose n equal to 3? No, because the requirement is n must be even. Okay. So 2 is fine. I mean, probably the worst approximation that you can generate. 2 is the bare minimum. Even with 2 steps, I am able to match this exactly. No error. Let me show you the sum. So it's the sum product of this vector and this vector multiplied by h by 3, right? That's the formula. And it is giving me the exact value. There is a question coming in. If Simpson's approach is a good approximation, why Riemann sums cannot be solved? That's what I have heard. No, Riemann sum can be solved. It's just a rectangle area that we looked at, right? You can solve it. Uh, it's very simple. Maybe you are confusing with, there is another hypothesis called Riemann hypothesis, which is an unsolved problem in mathematics. If you solve it, you'll get $1 million. Like literally, there are 7 unsolved problems in mathematics. One of them is Riemann hypothesis, which is very different. It's nothing to, it's part of complex analysis. Maybe you're referring to that. But what we are doing is Riemann sum as in addition, not the hypothesis. Okay. Yeah, if you're interested, just Google Riemann hypothesis. Okay. Uh right. So this is Simpson's rule. And the accuracy is remarkable. It's exact. Why is this happening, guys? Any ideas? Why the error is zero? Even if 2 steps, I don't even need to go to 4 steps. You'll get the same, obviously, you'll get the same one. Even if 2 steps, I'm able to get the exact value. Why is it happening? And behind the scenes, how does this algorithm actually work? It tries to interpolate subsequent points, consecutive points, using a parabola or a quadratic approximation, correct? The original function itself is quadratic. So won't it be a perfect approximation? I am using 2 parabolas to stitch this curve together. And in my parabola, there are three parameters, A, B, C. I can perfectly fit this curve. There is no error. Okay, that's why you see this exact. But if you take some other function, this will be approximate, right? Any other function, log x, sin x, okay, e to the power x. Okay, coming back to our, so this is Simpson's 1/3 rule, extremely popular. Okay, now, oh, didn't I give the convergence? Okay, the convergence of Simpson, I'll probably update it. The convergence rate is h to the power 4. So this is even more accurate, okay, compared to all the other that we looked at. That's why this is the industry standard. Simpson's 1/3 rule is your go-to strategy, okay? And implementing this particular sum is not difficult. It's very straightforward. The only thing is you have to ensure n is an even number when you discretize the interval. The next one is Simpson's 3/8 rule. 3/8 rule. Where does this name come from? Because if in the final formula you see a factor of 3/8. There we had 1/3, so 1/3 rule. Here we have 3/8. Now I have not given any derivation or anything. It's if you're interested, you can look at it. But the key difference is this one interpolates using a cubic function. That's all. There it was trying to interpolate using a parabola, which is a quadratic function. Here, with the approximation between the 2 points during the interpolation is using a cubic function. To use cubic function, we need 4 consecutive points, correct? So it can fit a perfect cubic function in 4 adjacent points. So let's say this is my curve. I need this point, this point, this point, this point. And we'll try to fit a cubic function that will pass through all the 4 points. The real function might be doing something more dramatic, right? It could be doing something like this. I'm just saying. But the algorithm will try to fit a cubic function passing through these 4 points. So obviously you'll ignore this area, overestimate here, and then underestimate here. But overall, it will be a very accurate scheme. Okay. And how does the formula work? Oh, before that, there is a requirement. N must be a multiple of 3. The same idea because we are using 4 points, right? N has to be a multiple of 3. 1 point is shared, right? And if you look at the final formula, so we have 3h by 8, y0 plus yn. They have the same coefficient of 1. All the multiples of 3, and this last one is also a multiple of 3 because n is a multiple of 3. All the places which are multiple of 3 receive a coefficient of 2. Everything else receive a coefficient of 3. Okay, y1 plus y2, y4, y5, y7, y8, all of those will come here. So this group are multiples of 3, and this group is everything else. Well, of course, the first and the last one are handled separately, so that is always there. That's Simpson's 3 by 8. Now, if you ask me, the from an adoption perspective, this rule is not as popular as 1/3. They are accurate. There are cases in which one rule could be better than the other, but 80% of the time you'll probably use 1/3 rule. Okay, not the 3/8 rule. It's more restrictive. The n has to be multiple of 3, right? So ensuring n is even is a little better than ensuring n is a multiple of 3. So here is the uh, implementation of the same. Yeah, so here I've taken x4 to get an approximation. But the main thing is you have to just ensure that this is the basic stuff. Calculate the f of x. If you look at the coefficient, the first one, so there are 60 steps here. Let me make it 6. 6 is an allowed number because this is a multiple of 3. We need something that is a multiple of 3. So this is fine. First coefficient is 1, last coefficient is 1. Then we have, for y1 it is 3, y2 it is 3, but for y3 it is 2. Okay, and this process continues. And then take a sum product of the coefficients and the heights. That will give you the term inside this bracket. Then finally multiply a 3h by 8. That is what I have done. This 3h by 8. All right. So this gives the approximation for the area under the curve. One thing I forgot to mention is, so we looked at Simpson's 1/3 rule. It can exactly approximate a quadratic function's definite integral. In fact, it can also approximate exactly a cubic function. The region is really technical, so I will not give you the derivation, but you can, there is plenty of literature available online. You can take a look at it. Even if you have a cubic function, right, it can be any, general cubic function. 3x cubed minus 5x squared plus 2x minus 6 integration. With Simpson's 1/3 rule, you can also exactly calculate the area under the curve. Okay, it supports, basically it remains exact till cubic, the cubic order. All right. But remember, it uses an interpolation which is quadratic, but the approximation of the entire the area under the curve goes till the cubic polynomial. And then we have, yeah, when it goes to 4th degree, there it will not be exact. So with 60 steps, you get an approximate value, 6.4. 40003, right? There's some error, right? Beyond cubic. Okay. And finally, there is a comparison that I've done for this particular integral. So our function is f of x equal to 1 by x. We know that the integration of 1 by x, this is our definite integral, 1 by x dx from 1 to 2. What is the value? Integral 1 by x dx 1 to 2 is equal to log x 1 to 2 log 2 by 1 log 2. And please remember, log 2 is 0.693. Okay, this is an important value, so we need to remember. Okay, so here I've done a comparison. I've taken 6 steps. You know why I have taken 6 steps? To compare among all the algorithms. Okay, left sum, right sum, midpoint sum, trapezoidal rule, Simpson's 1/3, Simpson's 3/8. Why have I taken 6 steps? Who can tell me? Are you guys there? Anyone? Why have I taken 6 steps? Why not, let's say 8? Yeah, exactly, right. So if I want to use Simpson's one-third rule, I need n to be an even number. And if I want to use Simpson's 3/8 rule, I need n to be a multiple of 3. The lowest number that can satisfy this is 6. That's why I'm taking 6. You can take any other value, 12 or 60, whatever. So with 6 steps, let's see the numerical accuracy of all these schemes, right? So here are the indexes. These are my x, and x mid you can calculate. This will be needed for the midpoint rule because you have to evaluate the function at the midpoint of these regions, which is on at these points. So here I have f of x, f at x mid also is there. For the left hand sum, the weights are 1 actually. It's a simple sum if you remember, because we are just adding the heights times the fixed width, and it gives the equal weightage to all these heights, starting with the left one. So everywhere in every region, it is the left one that gets the weight. The last height will not get any, will not be included in the left hand sum. For the right sum, we take the right side, right? So it'll include all these values, and ignore this one. And for middle sum, the weights are 1, but it is multiplied with f at x mid. Okay. Trapezoidal rule. Remember, the first and the last receive a weight of 1. Everything in between is 2. Okay, because double counting. And then one-third rule has this one, right? 1, 4, 2, 4. 1 and 1, then alternate between 4, 2, 4, 2, 4, 2. And this is 3/8 rule. Okay. And using this, I got the results here. The exact value is 0.6931. This is log 2. Okay. Log 2 is 0.693147, whatever. Left sum, right sum are the most inaccurate schemes because the convergence is h square. Mid sum, very accurate. It's better than trapezoidal. Okay. You can see yeah, see the error. It's half of this one. This is the best in these ones. Okay. And then Simpson's one-third rule, fantastic approximation, 0.693169. First 4 decimals are correct, right? And then 3/8 rule. Yeah, I'm not going to go into which of these is better. It's debatable, but I would use this always. Simpson's one-third rule. Okay. I have a little bar chart to show you the error comparison. I can increase n. By the way, you you can use actually, yeah, you should not use different values of n other than what is mandated by the scheme. So I can probably use, let's say, 12. And you can see how the errors are still going down, and yeah, the convergence. If I use maybe 60, so these are becoming extremely accurate. Okay. And this one is also, I think, not that bad. Obviously, these are more accurate than midsum. All right. Uh, yeah. Any questions, guys, before we take a break? Clear? Okay. Let's take a break. We'll meet after 5 minutes. There is one special algorithm that I need to cover, which is called the Gaussian Quadrature. Extremely, extremely powerful stuff. you will see the level of accuracy. Okay. Let me see if I missed anything. No. So we'll start from here. Okay, let's meet after 5 minutes. All right, so now we'll look at a very, very special algorithm given by none other than Mr. Gauss, right? It's called Gaussian Quadrature. And you'll see the power of this. So yeah, so all of this stuff is in the slide. You can refer to that. Let me walk you through the idea of Gaussian quadrature. Audio check, guys. Can you hear me? Okay, all right. Allow me 30 more minutes to wrap this up. It will not take much more time. So till now, what we have seen is all of these numerical algorithms ultimately are of the form of this form, h times sum of I equal to 0 to n, some kind of weight given to the value of the function at I. Correct. That is our structure that we have used so far. All of these rules. Um, okay. Except probably the midpoint rule, which is a little different because you have to average the x first and then evaluate the function. All the other algorithms are basically aggregation of the, so you have to find out the sample points, x0, x1, x2, xi, and then xn. Okay, this is A, this is B. And the curve is something like this. We don't know, but ultimately, when you're doing a numerical sum, the height at each point, which is f of xi, you are taking that height with some weight. The weight is sometimes 1, right? Remember, here the weight is 1, here the weight is 1 in Simpson's rule and other places also. In the middle, the weights could be either 2 or 3 or 4. We have seen all of those, right? So if you look at the big picture, it's just a sum of weighted sum of the function values at different points. That's all we are doing. Until now, we've been dealing with uniform spacing. We had a fixed spacing, h equal to b minus a by n, equal subintervals, equal width, you can say. That was our assumption till now. But why restrict that, right? Why don't we use some flexibility in terms of deciding where do we actually sample? Okay, doesn't have to be this strict regime that we have to divide it into equal subintervals. We can do it non-uniform also. Okay, I'll give you a hint. If the function is a straight line, suppose we have a linear curve, okay, does it even matter if it's a perfectly linear curve, right? Truly speaking, how many points do you need to evaluate the function to calculate the exact area? Think about this. We have a point here, x0. This is xn. How many region? So we already have the values here. This value is there. F of x0, f of xn. How many points do you need to divide the region into to, get a better approximation? If it is linear, then do you really need those many sample points? You don't exactly. You need only 2 points. Beginning, end, that gives you the slope. This is completely defined. There is nothing, no room for any kind of error, right? But if the curve is going crazy like this, something like this, then you need to divide it into much, much smaller segments so that you can accurately add up the, right? So it has to do with slope and curvature, right? If a curve is pretty much, so look at this curve. So from here to here, it's almost like a straight line, right? So why do I need so many intervals? Maybe I need a point here and I need a point here. This becomes like a trapezium to me. Perfectly, I only need this point and this point to approximate this segment. I don't need a million different points. Okay. So the point is, if I have fixed limited resources in terms of points, let's say I'm allowed only 10 points. I can choose any 10 points I want, get the value of the function at those 10 points, and then somehow find out the area under the curve. I can use these resources a little more efficiently. Okay. I don't have to do equal spacing all the time. Okay. Wherever the function has a lot of curvature, probably I'll use more points there. If it is behaving linearly, then I don't need so many points. Okay. So just giving you a very, intuition, why this whole idea of how this Gaussian quadrature came into being. Okay. So the big breakthrough here is I am not bounded by uniform spacing. So I can choose my x size as flexibly I want, wherever I want. It's up to me. Okay. I will choose where to evaluate. So if I have this is my function and this is my interval a to b. If I'm given 3 points, maybe I'll choose this point and maybe let's say here 3 points, x0, x1, x2. Okay, because this part is pretty much linear, let's say. And then for this part, I need a little more approximation. I'm just saying, if you have 3 points, maybe I'll distribute like this. I don't have to have one exactly at the middle, right? So that is my first flexibility. Choosing x size is up to me. Then the weights, that also I have free. I can devise any weighting scheme I want, right? We saw that for different algorithms, the weights are different. So that is also up to me. So here I can exercise the flexibility of number one, choosing xi, where I want to sample, and then the corresponding f of xi, obviously, correct? And the second one is weight of f of xi. Okay, so I can choose this. Now using this idea, let's slowly develop the formula, and then I'll show you what the people have done over the years, and you will see how accurate this stuff is. Okay. Before we proceed, we'll look at this one, a fundamental integral. We'll only focus on this integral, ft dt from -1 to 1. This is what we will focus on. I mean, all the formulas and everything that we derive will be for this specific definite integral. Then you will say, sir, then how does it apply universally for any kind of definite integral? Well, any kind of definite integral can be transformed into this integral, ft dt. So in general, we have this question, right? Integral f of x dx from a to b, correct? I can convert this integral to this integral by doing a intelligent substitution. Okay, let's quickly do that. So we are given this, okay? Substitute x equal to just a variable transformation, b minus a divided by 2 times t plus a plus b divided by 2. This is my substitution. If x is x is a linear function of t, okay? Now let's see what happens. So what is dx by dt, guys? Dx by dt is simply b minus a by 2. All right. Now let's evaluate the limits. X goes from a to b, correct? In the original integral. So t will go from where to where? When x is a, t is what? And when x is b, t is what? Can you tell me when x is a, what is t? Basically, you have to substitute a here and then see what t becomes. When x is a, what is t? You can do it on your own, but let me give you the number. T is actually -1. It's probably easier to put t equal to -1 and verify. So if you put t equal to -1, what happens? You get minus b minus a by 2 plus a plus b by 2. That leads to a, correct? A by 2 plus a by 2. If you put t equal to +1, you can clearly see that a by 2, will get cancelled. You'll get b by 2 plus b by 2, which is b. Okay. So my original integral indeed became this integration of f of x is now this big function of t, but it's fine. It's just a function of t. It's a new function of t, right? It's not ft. It is f of, there is t inside. So we'll look at one example. It's fine. Then instead of dx, I can write b minus a by 2 dt. So b minus a by 2 is a constant, will come out. This becomes dt. And the limits have become -1 to +1. Okay. So that's how I can transform any definite integral from a to b to, doing a variable substitution. It's a new variable. And the integral goes from -1 to +1. Okay. So look at this part. There is a constant multiplied outside, which is no big deal. We can always multiply. So, right? So now that we know this, we'll only focus on this one. How do we evaluate this integral as efficiently as possible? Okay. So here is our integral, -1 to 1. I'll show you one concrete example after the theoretical derivation. I'll show you one example. So we are focusing on this. Okay. Now consider, let's say we have a case where it is linear. Linear? Ft is a linear function. Start with the very simple one. Ft is linear. So I want to devise, and okay, Ft is linear. The functional form that, let me write it like this. So I want to do this. Integral -1 to 1 Ft dt, right? This is my task, okay? And I want to approximate this integral by using, remember, weight times value of the function at some point, correct? I will use just one weight and value of the function at some point t0. Okay, so if you look at this plot, ft would be some curve, right? I am using just one sample point anywhere I want, t0, and the functional value at t0, ft0. And there is a weight also, w0, which I am free to choose. Can I make this work for a linear function? Okay, ft is linear, so it doesn't look like this, it looks like a straight line. Can I choose w0 and t0 in such a smart way, that this is not even approximation, it is exact? Okay, so let's do this. First condition is, condition A, ft, I should be able to use this till degree 1. Okay, so that includes ft can be either a constant or it can be a linear function. Okay, till that point I should be able to use this approximation. Remember, right hand side is our structure of approximating, right? Weighted sum of value of the function at different points. Here I've taken only one sample point t0. This needs to be chosen magically, where I need between a to b, I need to choose t0 in the smartest way possible. Just one sample point. And value of the function I can calculate ft0, and weight is also something I can choose. And can I make this work? Okay, for a linear function. So ft is a constant. If ft is a constant, then let's say ft equal to a0, some constant. So what does this integral become? A0 dt -1 to 1, which is 2a0, right? This must be equal to W0 times ft0. Now, if ft is a constant, which is always a0, no matter where you sample, it will always give you 2. Oh, sorry. It will always give you a0. Are you with me? So I'm trying to match this exact integral with this approximation. I mean, the numerical sum, it is an exact match, right? That is what I'm trying to achieve. The two parameters I can choose, W0 and T0. If ft is a constant, then it will be of this form, ft equal to some a0, constant, always constant, everywhere constant, something like this, a0. Okay. So I'm saying this integral goes from -1 to +1. The true integral value is 2a0. a0 will come out, then integration of t dt is t. Apply the upper limit 1 minus -1, which is 2, which is 2a0. This must match my specification, which is w0 times ft0. F is a linear function, so no matter where you choose t0, here or here, the value of the function is always a0, right? So ft0 is a0 times w0. Okay, this is my first equation. Actually, my first equation is a0 get cancelled. W0 is equal to 2. That's a nice result. So my weight must be 2. That is what I just derived. I've still not figured out where do I place T0. In a constant case, it does not matter, where you can sample at any any point and then get the value of the function, which is nothing but A0, multiply 2, you are done. Okay. Case B, ft is linear. Okay, this recipe will work till the first degree, so till linear terms. So ft must be of this form, something like, let's say a0 plus a1t, correct? Linear function of t. Now what is this integral? A0 plus a1t dt minus 1 to 1. We are trying to approximate this as w0 f of t0. Okay, just one sample point you have to choose. W0 already we have solved, it is 2. Now the question is, where do I choose T0? Because if it is linear, then it is not arbitrary. It will be a specific point where you have to sample it. Okay. Now, can you help me with the integration? We know that a0 dt integration from -1 to +1 is 2a0 plus what will be the integration of the second part? Please try it out and tell me. a1t dt integral from -1 to 1. a1t dt integration from -1 to 1. Sachin says 0. It is 0. Yes, it is 0 because it will be t square by 2, correct? And when you put the upper limit is 1 by 2 minus, when you put the lower limit -1, it's -1 square. Again, it becomes 1. So 1 minus 1, which is 0. So that is correct. In fact, if you know this powerful theorem, any odd function we have, which however it looks on this side, it looks the exact opposite on this side. If you take the integration from -a to +a, minus, let's say minus k to +k, area under the curve, right? This will be a negative area and this will be a positive area. They will completely offset each other. You get a 0. Okay, integral -k to +k, any function f of x dx. If this guy is an odd function, then the integral is 0. a1 times t is an odd function because the graph is like this. right? So the areas get cancelled, perfectly cancelled from -1 to +1. So this is again 2a0, right? So we get 2a0 equal to w0 f of t0. Okay. um, right. So from here, what do we get? So what is f of t0? W0 is 2, we know, we already solved it before. For constant case, W0 must be 2. The same thing we are carrying forward. F t0 in linear case is a0 plus a1 t0. You can clearly see 2a0, 2a0 gets cancelled. T0 is equal to 0. T0 equal to 0. Only then this will be satisfied. So we finally found that W0 must be 2 and T0 must be 0. Using this combination, we can exactly calculate this integral. No error. Up to linear term, this integral, any linear equation you take, this integral is simply 2 times W0 times f of t0 is f of 0. That is powerful stuff, right? Any linear function you take, so this is for linear case. Any linear function's integral from -1 to +1 is given by 2 times value of the function at 0. What, really? Let's verify this. Do I have enough page? Maybe I'll take another page. So we are saying -1 to 1 integral ft dt is 2 times f of 0 if f of t is linear, something like this, a0 plus a1t. Example, let's say, what should we take? -1 to 1, any linear function, 2t plus 4, for example, dt. What is the integration of this? Remember, the odd part will vanish, right? So we only have the even part. 4 times 2, which is 8. This is the integral. Let's apply our shortcut 2f0. 2 times value of the function at 0, which is 4. Matches? Exactly matches. Any questions? So till linear term, right? Constant or, constant plus slope, we can calculate area under the curve in one shot. This is just sampling at 0. What is the value of the function at 0? Times 2. This is the weight. And we chose the xi to be at 0. Don't sample anywhere. Sample at the point 0. Get the value of the function multiplied by 2 gives you the value of the integral. That is awesome. Did you understand this idea? It's a very simple argument. And we also verified it. Any questions on this before we move to the next one, and then we can generalize? Clear, everyone? Okay. Let's move on to let's add more complication. Case 2. Let's consider till cubic. Till cubic. So we had till linear, right? Now we're talking about till cubic. Why till cubic? Why not quadratic? Well, cubic is a superset, right? And we will enhance our specification. We'll have more degrees of freedom on the right-hand side. And it will work till cubic. Okay. So if the coefficient of x cube is missing, automatically cubic will become quadratic. So it will cover quadratic and cubic together. Till cubic, we can have this, right? So our function is a cubic function. The general formula would be a0 plus a1t plus a2t square, a3t cube, a cubic function. Okay. Now we're trying to do this stuff. Integral of any cubic function from -1 to +1 can be approximated by this sampling scheme here. one weight and one x will not work. We need two terms. Okay, just extending the right, because you see it's very natural. In a linear function, you have two parameters a0, a1 on the left hand side for the exact integral. On the right hand side, we also need two parameters so that we can match it exactly. And the two parameters were w0 and t0. Okay. For cubic, we have how many parameters? A0, A1, A2, A3, right? Any cubic function can have these four different parameters. They will behave differently. So on the right-hand side, we also need four terms. And how will that look like? Let's say W1 FT1 plus W2 FT2. So we have any cubic function. I don't know, something like this maybe. And we're trying to evaluate the integral from actually, it's -1 to +1, right? Let's do this. -1 to +1. We're trying to find the area under the curve, right? That is the left-hand side. True integral, correct? We are approximating by only sampling at two different points. Let's say my T1 is somewhere here and T2 is somewhere here. Get the function value here, f of T1. Get the function value here, f of T2. Use some magical weights, W1 times FT1 plus W2 times FT2. That will give you the exact area under this entire curve. Sounds extremely, extremely efficient, right? Is it even doable? It's doable because there are four parameters here and the four parameters on the right-hand side. So by suitably choosing where I need to sample and where and how much weight I need to give them, I can do this. Okay. So it is a little more involved, but let's go through this exercise and then we'll look at one example. I'll show you how accurate this stuff is. Now my functional specification has changed. I have two W's and two T's, right? So we have to do the whole exercise all over again. If ft is linear, no, not linear, constant. Okay, which is, let's say, ft equal to a0, right? Then integral ft dt will be 2a0. We did it last time. That must be equation 1, w1 ft1 plus w2 ft2. But if ft is linear, then no matter where you sample these values, ft is always a0, right? Constant. So I can write w1 plus w2 times a0. And my first equation is w1 plus w2 must be equal to 2. Equation 1. I got this from assuming that ft is constant, then this must be true. Next, if ft is linear, then it must be of this form, a0 plus a1t. And we know the left-hand side integral is still 2a0, correct? Because the odd term will vanish. And that is equal to w1 ft1 plus w2 ft2. And this is equal to, in our case, it will be w1 a0 plus a1 t1, correct? Because you are sampling at t1. We don't know what that is yet. W2 times a0 plus a1 t2, right? And this is w1. So if you take a0 common, you get w1 plus w2. W1 plus w2 is 2, so this is 2a0, correct? Plus take a1 common, you get w1 t1 plus w2 t2. This also gets 2a0 to a0 gets cancelled, and we get this beautiful second equation, w1 t1 plus w2 t2 must be 0, correct? Second equation. How many parameters you have to solve? There are four parameters. What? W1, W2, T1, T2. We have to have four equations. We got two equations, okay? And then we keep going. Let's do a C ft is quadratic. Remember, this infrastructure will support till cubic, right? So 4 parameters, 4 unknowns. If it is quadratic, then it must be a0 plus a1t plus a2 t square. Okay. Now, if you do the integration ft dt from -1 to +1, well, remember the constant term will give 2a0, correct? This term will vanish because it's an odd function. What about the last term? Can you quickly tell me what is the integral? Integral of a2 t square dt from -1 to +1. Integration will be t cube by 3, correct? And then in place of t cube, you need to replace 1, then do a minus, and then also put a -1 there. So what will be the answer? Try it out, guys. It's very simple. Two a2 by 3. You forgot the 3. One, there will be 1 by 3, right? T cube by 3. So 1/3. That will come out. 2a2 by 3. Okay. And this is equal to. So we have W1 FT1. In place of FT1, I'll write A0 plus A1T plus A2T square. Actually, this is T1, T1. Then sampling at T2, this will give me A0 plus A1 T2 plus A2 T2 square. Okay, now if we compare this, again, 2A0, 2A0 will get cancelled because W1 plus W2 is 2, so 2A0 will get cancelled. And if you take A1 common, right, you get W1 T1 plus W2 T2, which is 0. So right hand side, the 2 will get cancelled. We get 2A2 by 3 equal to, if you take A2 common, W1 T1 square, W2 T2 square. So from here, my third equation is W1 T1 square T2 square equal to 2 by 3. Okay, equation 3. All right. So this is a homework for you. If you try for the cubic equation, do the exact same stuff, compare the coefficients, you'll get another equation which is given as W1 T1 cube plus W2 T2 cube equal to, can you guess what should this be equal to? Just an intelligent guess. Look at the pattern. Any guess? 0 exactly. So you get alternate zeros essentially. Okay, 4 equations, 4 unknowns. I'm not going through the solution procedure, but you can verify. So you'll get W1 equal to W2 equal to 1. Remember, W1 plus W2 must be equal to 2, correct? And turns out they have to be equal also. Okay. And T1 will come out as 1 by root 3, and T2 will come out as -1. -1 by root 3. Doesn't matter, they're symmetric. Okay. So what is this saying? This is saying that if you have any cubic function, let me make this T1 and T2. T2 doesn't matter. It's saying you just need 4 data points. One is value of the function at 1 by root 3, value of the function at -1 by root 3, and the weights are just 1 and 1, correct? So ultimately what I'm saying is integral ft dt for any cubic function from -1 to +1 is given as w1 f1. W1 is 1. So this is a f of -1 by root 3 and f of 1 by root 3. How nice. Any cubic function integral from -1 to 1 is given as value of the function at -1 by root 3 plus value of the function at +1 by root 3. That's it. And guys, mind one thing, although the right hand side emerged from our familiarity with the expression that it has to be a weighted sum of the value of the function, but it is not an approximation. It is exact. There is no error. It is completely, accurate. Okay. So in this manner, I can generalize higher and higher polynomials by choosing where to sample at and what should be the corresponding weights. Okay. And people have already done it. They have done it. So let me write a couple of expressions. For example, the next step would be what? Okay, fifth degree polynomial, right? Fifth degree polynomial f of t. Now, if I integrate f of t dt -1 to 1, I should write this as w1 ft1, w2 ft2, and another term w3 ft3. Okay, fifth degree polynomial will have 6 coefficients. So whatever that integration is, I can match it with my own 6 coefficients, 6 parameters, w1 t1, w2 t2, w3 t3. Okay, I can keep going. So you can see that with 1, 2, 3 terms, I can approximate a fifth degree polynomial. With 2 terms, we could approximate a cubic polynomial. Not approximate, actually, it's exact, again, cubic polynomial. So degree 3. With n terms, if I have n terms like w1 ft1, w2 ft2 up to wn ftn, what kind of polynomial can I approximate? What is the relationship? With 2 terms, we have a coverage till 3 degree. With 3 terms, we have a coverage till 5 degrees, right? With 4 terms, we'll have a coverage till 7th degree. So what's the relation, guys? With n terms, we can cover till 2n minus 1. 2n minus 1. Okay, degree polynomial integration we can calculate. Exactly. Exactly. Okay. Now, I went online and I found a table that has 64 terms. 64 terms. People have done it and they have evaluated all the weights and the sampling points where you need to sample, what will be the weight for 64 terms. Okay. So this gives me a coverage till 127 degree polynomial, right? One moment. Okay, I'm back. Sorry about that. So I hope you understood this. Let's look at the table and look at one small example and we should be good. Okay, all the derivation and everything that I did is here for your reference. You can look at it. Okay, so let me go to Excel. This is the table that is available publicly. It is published. It's just a lookup table. We can use it. Yes, so Sachin brings up an important point. Till now, we have looked at a numerical recipe to compute the exact definite integral for any kind of polynomial, correct? But we are not dealing with polynomial all the time. There would be functions like sin x, log x, cos x, e to the power x. But here is the thing. We are using the value of the functions, right? To sample, whenever we are sampling, we are getting the value of the function. Instead of actual cubic function, you might have a log x function, but you will evaluate log x at those sample points based on our published results. Now, any kind of function, continuous differentiable function, can be viewed as a rich polynomial. Exactly, or it says Taylor series. So Taylor series is a mirror to look at any function, e to the power x, log x, sin x, anything, as a high degree polynomial. The more terms you take, the better approximation you'll get. And we have done this. We have approximated many functions using Taylor series. So if you use an infinite degree polynomial, it can fit any kind of transcendental function exactly, right? So that's pretty much it. So we can pretend that every function is a polynomial, high degree polynomial. So we'll take more terms and just get, use the result that we derived, assuming that our core function is a polynomial. But even if it's not a polynomial, if you're using higher and higher order, you are approximating that function as a polynomial. It exists, so it will still work for other functions. So that's the beauty of it. Okay, for polynomial, it will be exact. For other functions, it will be approximate. Okay, so how do we read this table and use this table? So what I've done here is, for n equal to 2, 3, 4, 5, you can see, what do I need? I need where I need to sample, what will be the corresponding weights. Okay, till for n equal to 2, 2 means I have two terms. So W1, fx1, W2, fx2. With two terms, I can go till which degree polynomial? Remember, what was the approximation for which polynomial we had this approximation W1 f of t ft1 plus W2 ft2? Yes, 2 times 2, yeah, correct. 4 minus 1, 3. Cubic for cubic polynomial. So this gives me coverage till cubic polynomial, right? And what are these values? These values, 1 by root 3 minus 1 by root 3, we just calculated, right? The weight needs to be 1. See, this is the representation. Right? For cubic polynomial, the weights are 1 and the value of the function needs to be evaluated at 1 by root 3 minus 1 by root 3. That is what this is. Okay, this is minus 1 by root 3, this is plus 1 by root 3, the weights are 1. If you want to calculate the area under the curve of a till which, if I have 3 terms, I can support till 5th degree polynomial. For a 5th degree polynomial, I need 3 sample points. What is the value of the function at 0? Value of the function here, minus 0.7446. Value of the function here. 3 values, 3 weights, sum product, you get the area. Of a 5th degree polynomial, just 3 points. You need only 3 points on the curve and you can calculate the entire area under the curve. Provided your limits are from -1 to +1, but that's not a big deal. Remember the transformation? If you're given any integral from a to b, we can convert that integral to -1 to +1. Okay, I'll show you one example how we can do that. So you understood how to read this table? I'll give you this Excel. I copied the values till 25, but you'll find the lookup table till 64. And that is more than enough. I'll show you how accurate this is, okay? Even with few sample points, how we can approximate. Okay, so let's look at one example and we should be good. Any questions on understanding or interpreting this table? How to use it? No questions? Okay, cool. So let's look at one example. The same example that we had, comparison, remember? Our function was 1 by x. This is not a polynomial, right? It's x to the power -1, which is an infinite series of polynomial. There are infinite terms. Anyways, The exact integral is log x. So from 1 to 2, it becomes log 2, which is 0.693, ln 2, 0.693. This is the exact value. And we saw all of these things, right? With 60 steps, I'm getting, let me make this 8 steps. Well, this one will not work. Multiple of 3, right? So let me take 6 steps. Question mark is, what if function is not defined on those prescribed points? Yeah, that's a given. So you have to know the value of the function. How would you integrate if the function is not defined? The integration doesn't exist, right? Function must be continuous. It could be a step function also, but the value of the function would be there. Otherwise, the integration would not exist. How would you calculate the area under the curve? So that's a given that it's the function exists at all those points, wherever you are calculating the integral. All right. Okay. So with 6 steps, my traditional algorithms give me this kind of accuracy, right? You can see Simpson's 1/3 is 0.6931, accurate till the fourth order, fourth decimal. Now let's use Gaussian quadrature. Okay. So first and foremost, we need to do the transformation. Okay. So let's do that. So our ask is integral 1 to 2, 1 by x dx. This is our question. Hmm? Remember, we need to substitute x equal to b minus a by 2 times t plus b plus a by 2, right? That's a linear transformation. What is b and what is a? B, so my x is now given as 2 minus 1 by 2, so t by 2 plus 2 plus 1 by 2, 3 by 2. This is my transformation. Or I can write t plus 3 by 2. Now remember, what does this integral become? There is a, let me go back. Right? So if you see this integral, it becomes this integral. F of b minus a by 2 times 2t plus a plus b by 2 dt, limit becomes -1 to +1, and there is a constant that goes outside, which is b minus a by 2. Okay. So when we do this transformation, it will become integral -1 to +1, right? And we have f of this stuff. Okay. So t plus 3 by 2, it will become t plus 3 by 2 inside. Correct? That's the transformation. But what is f of t plus 3 by 2? F of x is 1 by x. So what is f of t plus 3 by 2? It is 2 by t plus 3. Correct? So my new integral after the transformation is this. I missed something. The constant outside, remember? We have a b minus a by 2 outside, which is half. Okay, after this substitution, x equal to t plus 3 by 2, this integral transform to this one. You also don't need the formulas that we derive. We can do it here, right? So integral 1 by x dx, right? What is 1 by x? If x is t plus 3 by 2, 1 by x is 2 plus 2 by t plus 3. What is dx? Dx is b minus a by 2 times dt. B minus a by 2 is half, and this is dt. And when x was 1, t was -1. And when x goes to 2, t goes to +1. You can check it. So if put t equal to -1, you get 3 minus 1 by 2, uh, which is 1, right? So when x is 1, t equal to -1. When you put t equal to +1, it becomes 3 plus 1, 4, 4 by 2, which is 2. So x equal to 2. When x equal to 2, t equal to +1. Okay. So all checks out. Now we spent a lifetime focusing on this part, correct? Any integral -1 to +1, ft dt. Our ft is now this 2 by 3 plus 2 by t plus 3 dt. Now, is this a polynomial? No, Sachin, to your question, it'll be actually an infinite series, okay? Because t plus 3 to the power minus 1, that will have an infinite expansion. But doesn't matter. We will pretend this is a polynomial. What degree? Is truly speaking, it is infinite degree, but we will keep adding higher and higher, more and more terms to get a better approximation. That's the whole idea, right? So yeah, I mean, just let's do this. Now I'll go back to Excel. So I've written it here, right? Ultimately, this original integration transforms into half integral minus 1 to plus 1 f of t plus 3 by 2. In fact, I can remove this and just directly write this is nothing but, oh my God, I am not able to see my ribbon. Give me one moment. So 2 by t plus 3, right? This is what we are trying to do. Okay. Okay. Now let's focus on this part and we'll just multiply a half at the end. All right. So how many points do we want to use? Let's say n equal to 5. 5 terms. 5 terms means W1 FT1 plus W2 FT2 plus W3 FT3 plus W4 FT4 plus W5 FT5. There are 5 points at which I'll sample this function. Obviously, I need 5 corresponding weights. So go back here. For n equal to 5, I need to sample that function at these points. And these are my weights. That is what I have taken. Okay, so these are my points and these are the weights. Value of the function, f of t plus 3 by 2, which is essentially 2 by t plus 3, correct? Because f of x is 1 by x. So that's it. That's it. So 2 divided by 0 plus 3. This is 2 divided by this point plus 3. Okay, so at these points, I'm evaluating my function. And finally, just a sum product of these two, right? W1 FT1 plus W2 FT2, W3, and then do a half. Okay, this is the sum product of these two. And the the approximation is sum product divided by 2. With 5 terms, the true value is this. And look at the accuracy. 1, 2, 3, 4, 5, 6, 7. It matches still 7 decimal points. I only choose 5 magical points on that curve where I have to sample from and the corresponding weights. And I'm able to approximate the integral by a significant extent. This is Gaussian quadrature, okay? If you want accuracy, go for this. But if you see these research papers, I mean, Simpson's 1/3 rule would be the second favorite, okay? But in Simpson's 1/3 rule, you don't need to store anything or do any lookup. It's very easy numerical procedure that you have to code, right? You know how the weights are derived, right? They alternate. So it's very easy to create a Python routine in 2-3 lines of code that performs integral using Simpson's 1/3 rule. For Gaussian quadrature, you need to store this lookup table somewhere and then do a lookup, fetch the points, fetch the weights, and then do a weighted sum. That's all. I can increase probably more terms. Let's use 6 terms. With 6 terms, I'm getting some, more accuracy. Yeah, you would. There are Python libraries. If not, there are definitely CSV files that you can put it in a local folder or something and just read it from there. I have not figured out yet because I have not looked at it, but I will have it ready. I'm pretty sure there should be some kind of library somewhere, maybe in SciPy or something. I'm not sure, but we'll look at it. Okay, so what I was saying is, if I go here, with 60 steps, If you look at the convergence, 69347, the true value, where is the true value? Oh, here. Okay. 1418. Let's not take 60. Let's take 12 steps. Okay, we need 12 sample points. Actually, 13 sample points if you include 0. And the Simpson's one-third rule is accurate up to 314, 1, 2, 3, 4, 5. 5 decimal points. Okay. And then it starts to differ. With 12 steps here, 12 sample points here, this is accurate up to, you can clearly see, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 14 decimal points. So clearly a winner. Okay. All right. That's pretty much what I had for today. So today we looked at deterministic numerical algorithms. Numerical integration using deterministic algorithms. Okay, we are dividing the region into different parts and then calculating the areas of the different regions, adding them up. Everything is deterministic. There is no random variable or distribution anywhere. Did you see any random nothing? No random, no stochasticity, nothing, right? So these are all deterministic algorithm, extremely powerful and useful, as you can see, right? If there are integrals which are do not have a closed form, then this is your fallback option, right? You have to use numerical techniques. There is an entire other breed of numerical algorithms which can be used to evaluate the integral. Okay, and that will also be our bread and butter going forward, and that is called, who can answer? It will not be deterministic. We will use stochastic procedures or random variables to calculate the integral. What is the tool? Name of the tool? Monte Carlo, exactly. So it's a completely different idea. We will use random numbers to get the area under the curve. Okay, and what is the significance of area under curve for a quant finance professional? Well, we have to price a derivative. Price is given by an expectation. Expectation is an integral. So we can use deterministic algorithms to perform the integration, or Monte Carlo, which is a random probabilistic setting. Okay. That's all. That's all I had. Any questions before we wrap up? All right. If no questions, then we are good. Let me know if you have any questions in the group. Have a nice weekend. Bye, guys.